And I'd like to welcome our keynote speaker, Yanjun Qi. Yanjun is an associate professor at University of Virginia. I'm going to give a short introduction for you, Yanjun, and then continue your slide. So it's an honor for me to introduce Yanjun Qi. She's an associate professor at University of Virginia, Department of Computer Science. Her research interests are in machine learning and its applications with biomedical impacts. She obtained her PhD degree from School of Computer Science at Carnegie Mellon University in 2008, and her bachelor with high honors from Computer Science Department at Shuanga University. I think I'm really doing a bad job in pronouncing the name. She was a researcher in, but I know that it's the top university in China, right?
Yeah, it's Tsinghua University.
Yeah. Tsinghua, yeah, okay. She was a researcher in the machine learning department at NEC Labs, Princeton, from 2008 to 2013. And she has served in many international conferences, workshops, and she has received Career Award from NSF and Best Paper Award at NeurIPS workshop for transparent and interpretable machine learning in machine learning, and which is the kind of the topic of today. And she also serves as Data and Technology Advancement National Service Scholar in NIH. And on a personal note, Yanjun is my academic elder sister. So we share a co-advisor, and she kind of paved the way for my PhD. And she can juggle many things at once, and she's very inspiring as a woman in computer science. And for the students here, I want to note that if you visit Yanjun's website, it's a gold mine. Not only the group work is organized in thematic topics, and the source codes and the papers are shared, but also you will reach out to research blogs about these topics that are also published by others, kind of online journal club. So she's always been that resourceful, and we are very happy to hear you today. Thanks for accepting our invitation.
Thank you, Osner. That's just such a flattered introduction. It's a great honor to have a chance to talk to you today. So can I start sharing my screen now?
Yes.
All right, okay. So in fact, the topic I'm going to talk about today, it's a little bit, it's like a subtopic from my original title. So specifically, I want to talk about a library we built recently called Text Attack. It's to generalizing the adversary examples to natural language processing. So the table, this is the roadmap of how I'm going to organize the talk, because this is a summer school. So I'm thinking there are a lot of students need a little bit background information. So I will mostly focus on the background introduction. So first, I'm going to talk about what is natural language processing and deep learning advances on natural language processing. Then I'm going to talk about what is even adversary examples and what are the definition in vision and what are the definition in NLP. And then the last part is about our work, the text attack. So why this text attack library is necessary? Okay, so let's get started. So what is natural language processing and the relationship to deep learning? So I hope this is not like overlap with other tutorials. So I will start from basics. Perfect. So natural language processing is a subfield of computer science. It's basically a combination of artificial intelligence and computational linguistics, and it concerning it just work on the problem to have a smooth interaction between computers and human natural languages. And it aims to identify the structures and the meanings of words, sentences, texts, and conversations. It's aiming for providing deep understanding of broader type of language types. It's not just one language, there's many, many different kind of natural language types. And you can actually tell natural language processing is all around us. So for example, the Google Translator, you must have been used it once or multiple times. It's just such a handy tool when you travel abroad or trying to read maybe literatures in other kind of languages. And then the dialogue system. So we actually use it a lot. So for example, like in most of the e-commerce website, you're going to be assisted by an automated online assistant, kind of backed up by this natural language processing technology-backed dialogue system. And also you may use Alexa, all this our personal assistant too in our in the phones, and they're providing natural language-based instructions. And also the other really popular use of natural language processing is the sentiment opinion analysis. So I went to this website called the Social Mention, but there are many, many similar websites. You basically just can put a search, a term that you care. For example, in this case, I love coffee, so I put Starbucks there. So it gave me, there's a recent Reddit post, what are the sentiment on Starbucks? They're positive, about positive 12, neutral posts about 12, negative posts about 5. So basically it's a pretty positive, kind of matches my impression too. So you just go to those websites, you can actually tell me what are the opinions, the sentiments of those products, maybe websites. I mean, this is such a handy tool, give us guidance. I mean, when we are exploring like information explosion. And then question answering. This is iconic winning of artificial intelligence technology is IBM Watson, Computer Wins the Jeopardy games. It's a very complex question answering game, but IBM managed to build this fantastic system to win the game. All right, so like last thing I want to share is the most simple but very useful task, text classification. You really use it every day when you're using emails. Your email system classifies the emails into spam or normal emails. Your email system also kind of classify, is this email has attachment or not attachment, or into different categories that you care, promotion type or maybe social types. So it's just such an important use of NLP, and hopefully this gives you a sense about how important natural language processing really is. Okay, so natural language processing is it's just all arounders. Now, how do we do it? So the classic NLP pipeline includes a set of components for understanding text. It normally starts from text segmentation, part of speech tagging, name entity extraction, event tagging, or like a few more, like what sense disambiguation or syntactic parsing. Just there's so many components, and we use linguist knowledge to decompose this really massive task of processing. So for example, like the simplest task, like part of speech tagging, I'm just trying to figure out each word, what are their POS tags? So in this case, which one is noun, which one is verbs, so on and so forth. So there are a little, like that's very basic. A little bit more difficult task is this tag called like co-reference recognition task. So how do I know is Chris Mr. Robin in this text? And there are many other tasks like information extraction tasks, like where is the person? So who is the person? What words mention the person here? What words about company? So about state, about like, and then you can convert after you extracting this entities and relationships, you can convert this unstructured tag into structured relational database entries to organize the text. So this is the classic NLP pipelines. And how do we handle this? And so we are really in part of this evolving revolution that deep learning is revolutionized the NLP pipeline. So basically, we can think about the whole thing as 4 phases. Before the deep learning era, and then inside deep learning era, there are 3 important milestones. So before the deep learning era, we have the supervised predictors for each of the components. And the classic technology normally make use of backward word representation, techniques like latent semantic indexing or topic models. And then starting from 2012, when the ImageNet competition realized the deep learning, the power, so powerful, such a powerful group of machines. So we start to, and in 2013 and 2016, and then we start to have the first deep learning revolution. So that approach is called word to vect. And then concretely is trying to solve the problem. So Osno, can you hear my AC sound? Really loud AC sound?
No, I don't.
You don't? Okay,
but
then that's good.
I think, but we don't. Yeah, we are.
All right, and then we are good. All right, so how to represent the word. So the basic question is trying to solve is how to represent the word. And the fundamental idea is to convert those, the classic binary vector-based representation, which is extremely high dimensional, extremely sparse, into this dense numerical representation, which people call that distributional word embedding based representation. So the old, the sparse high dimensional representation have very few signals. You really basically don't only know that's a dictionary term exists there. After you convert it, learn this good representation space, you're representing each word in this much lower dimensional space. And the distance among the words give you a lot of semantic meanings. So for example, in this case, the distance between men and women, it's very similar to the distance between king and queen. So you can actually tell based on the distance itself, you can tell a lot of semantic relationship among words. So this is a very revolutionized concept, and it kind of enabled the NLP to be represented nicely into this deep learning architecture. So, all right, so now we have the representation into a low dimensional space. Then the next issue to solve is the classic problem in text representation is text is variable length. So how do we represent this variable length text segments? And then that comes from recurrent neural networks. Recurrent neural networks are networks with loops in the architecture. That loops architecture enables the information to persist. And this enabled us to do many, many things to representing the text. So for example, we can represent one word and to generate multiple words like text generation. We can enable the task, many words goes to one word, which is a text classification task. And the third thing I'm showing here is a many words to many words. So I have input many words, output many words too. So basically, this is exactly a machine translation task, right? You have a sequence of original language words, and then in the output, you have a sequence of the targeted language words. So this many-to-many architecture is a very important architecture in deep learning for NLP. So people call that seq-to-seq models. And so the input part, we normally call that part as encoder. And the output sequence, we normally call that decoder. So seq-to-seq is the decode encoder to decode architecture. All right, so this is the second really important milestone of deep learning on NLP. Then now we move to now. So starting for 2012, there's a really important concept called attention. So basically the attention was introduced to improve the sequence-to-sequence model, which we just introduced. So the attention mechanism is a really handy approach. So rather than when I'm generating the output sentences, like word by word, so rather than looking at all the history of input sentence word uniformly, I'm trying to have different weights. So this makes a lot of sense, right? When you're trying to do motion translation, my kernel words really not about all the words in that input, like original language sentence. It's about only a few words. So, but the structure of those words really depends on the language, the original language, and also the targeted language. So this attention weights provides you with such a handy, it's really handy and flexible structure that in this case we can tell. So I'm trying to generating a target language like word 2, the second language trying to translate from the original language. So rather than looking at all the input sentence, in this case, there are 5 languages here, or 5 words here. And rather than looking at them all the same importance, I'm trying to use this attention weight, which represented as alpha 1,2, alpha 2,2, alpha 3,2, alpha 4,2, alpha 5,2. They are different numbers. Actually tells me how important each word is actually to my current generated word, which is Y2. All right, so this attention, so this attention is actually from the encoder to the decoder. And now people actually pushes this even more. And so rather than I'm just only have the attention to other sentences, other sequence, other words, let me just try to figure out the words in myself. So this is such a great idea, trying to kind of improve this whole composition of different words into better representations, and then which is called self-attention. So I'm going to leave the details for you. If you are interested, just use self-attention. There are many, many papers. And so the thing I want to emphasize is this transformer architecture. Transformer basically just use 3 kinds of attentions. It has the encoder side of the self-attention, decoder side of the attention, and also plus this original encoder to decoder side of the sets of the this cross section attention. It's just totally attention based. It has no recurrent neural network at all, but it gives actually really great results. So people exploding this transformer architecture now, and the internet giants just having this bigger model and more complex structures. And Hugging Face is this in really fantastic website. They are training all kinds of transformer models and on different kinds of tasks. And basically I searched there more than 8,000 transformer architectures shared. You can totally just go there, download and use it. So in this big category of transformer architectures, and they're pretty like well-known. There's the BERT model, and then recently is GPT models. So BERT model basically is just a transformers encoder stack. And the most important part of that kind of revolution or good techniques is how do you pre-train it? And the GPT model basically is a transformers decoder stack. And it's generated pre-training. And also I'm going to leave the details for you to look by yourself. So just one thing to remember is both BERT model and GPT-3 or GPT-2 and now GPT-3 and the later model, they can all be used for any downstream tasks. And basically you can just use them as the pre-trained weights and use the architecture, add a little bit of your that's necessary for your task, and you can use for classification, entailment, question answering is the similarity base here, and or maybe multiple choices question answering, which is really give fantastic results on many different kinds of NLP tasks. All right, so enough for the background on NLP. So now we move to our second module is adversary examples in vision. So before I talk about adversary examples, I want to review a little bit about basics of machine learning. So we normally know machine learning is to find models that can generalize from observed data to unseen data. So the observed part, I mean, how do you get the model is the training phase. And when you use a trainer model on the unseen data, that's the testing or deployment phase. So adversary example is about the deployment phase. So in this figure, I'm showing, so there's a panda image fit into a trained deep learning model. It's just predicted as panda. So people actually find there's really intriguing vulnerability of deep learning models, which showed in this figure. So I can just generate, I can add this kind of well-crafted noise on top of my panda image. So let's just call that delta. And this delta plus my original panda image will give me this X prime. X prime, basically, if you use your eyes, it's still a panda image, right? But when you fit into this trained deep learning models, it gives me this label as gibbon. So this is like really weird. Why, right? I mean, the image itself is still a panda image. Why it gives me gibbon? So this reviews a very big sub-literature in deep learning called adversary robustness of deep learning. And why do we care about this? The reason is like a following few slides. So because deep learning is really used in everywhere now, and it starts to be used in those security sensitive setting and also the safety sensitive setting. For example, in this case, we are going to, there are people, the computer vision is really pushing their ways into the medical domain. And the pathologists use the computer vision based classifiers to do the first round of screening. And let's just look at this image similar to the panda case. The original image is at this really, your eyes can recognize this kind of perturbations. And the recognition will be from benign to pathological. And then another extreme case, so like this kind of carefully crafted glass shape. And then if you add on top of someone's face, it will be totally classified into other recognized face. And this is very concerning if you think about, we all use our face recognizer to open our phones, and people even use it to open their doors of the house. So this is very, very concerning. This property of sensitive small noises adding to the image totally mess up the deep learning, just claiming really great, nicely performed deep learning classifier predictors. And that has a lot of security concerns, generate a lot of concerns. Okay, so now it's a good time to talk about why do we, so what are the adversary machine learning? So what are the phases of adversary machine learning? So we can think about adversarial machine learning is a combination of CQ computation and machine learning. And basically you can think of there are two tribes in this category. So there's an attacker side, there's a machine learning designer side. The attacker side basically trying to design attacks, trying to review the vulnerabilities. And the defender side is the machine learning designer trying to develop the defense strategies to make their deep learning or machine learning classifiers like to be robust. And there's a few terminologies here. So we call those smaller changes on top of the input called adversary perturbation. The generated examples, we call them adversary examples. And we call a program that repeatedly generate adversary examples as adversarial attack. And we name a model's resistance to adversary examples as adversarial robustness. So in the end, so because I'm a machine learning designer, my goal is to improve adversary robustness of deep learning models. But to be able to improve it, I have to first review it, right? Are there shortcomings, vulnerabilities to my machine learning models? All right, so let's come back to see this image. So if we see, assuming like we put our points in a two-dimensional simple space, so basically the X and the delta, X plus delta, that delta direction is the direction most vulnerable, that easiest, that's the shortest path that can cross the decision boundaries that your deep learning classifier learned. So how do we represent this in a mathematical term? So I assure you this is the, I think this is the one of the only two equations I'm going to show you. So don't worry too much. I'm not going to show you a lot of equations. So here, so how to find delta? And basically it's an optimization formulation. I'm trying to make fx plus delta, in this case, not equivalent to my original y prediction. So this is a misclassification term. At the same time, I'm trying to bond the size of that delta to be really small. So because the image representation is kind of numerical, we actually can use the p-norms. So like in mostly people use two norms and inf norms. We can use the p norms to bound the size of that delta perturbation. And there are many variations of adversary examples. I mean, you can feel free to check out the literature. Let's just look at the last column. So the last column, we can actually tell this one, I mean, if you use the BIM type, it's kind of have this noise everywhere, and your classifier will classify it as 4. And the other L2 norm, it's kind of adding noise very close to the one itself. It will be fold classifier classify it as 2. And the last one will generate kind of spotted noise. It also fold into a 2 prediction. So let's decompose this equation into 4 like important parts. So basically, finding adversary examples is an optimization task, and it includes 4 parts. So how to define delta, and how to define the size of the delta, how to limit the delta, how to define we fold the model. That is really that L function and maximization formulation really is. And then in the end is how do you optimize this? So there are 4 parts, remember that. And this is really how our text attack library really is. That's the 4 parts. Okay, so we already talked about the, in the image case, the delta is just a numerical image and very, very small. We can bound it by the LP norm. So we solve the first question and second question. Then what's the third? What is the L? So how do we define, we fold the predictors? So there are many existing variations of that. So we already see one is called untargeted attack. We just push the prediction to be not the same as the truth. And the other one kind is called targeted attack. We push the prediction to be a specific T that we just aim for. So this is called targeted attack. And you can also like convert that optimization formulation from this constraint formulation into a Lagrangian form, which is actually this form representing. Okay, so in the vision, how do you optimize it? So that's the first question. So basically people use gradient-based approach, and there's a popular method called fast gradient descent method, and which I put the equation here. And there's another very popular attack called projected gradient descent-based attack. So the reason why you actually can solve that objective function that you define, which in this case, we always use the L to represent it, is the input space is a numerical space. The gradient is really indeed the best direction that cross the decision boundary. So if you still remember the definition of gradient, you're going to understand this Y gradient is the best direction in this case. So, and also there's a little bit of words here. So why do we care about fast? So this is actually related to the last, which I'm going to talk about, about text attack. So the final goal of using adversary examples is to improve performance of the trained model, right? So there's a basic technology called adversary training. So adversary training uses both clean examples and the adversary examples to retrain the model. If your adversary attack is too slow, you will not have enough example generated. So that's the reason why we actually aim for when you use adversary attacks to improve the model, to improve the model, a fast generation method is more preferred. All right, so we finished the second module of the adversary example definition in vision. So if you have questions, just put in chat. I think Osner can can just read it out and later. So now it's the third module about adversary examples in NLP. So first question is, why do we care about trustworthiness and robustness of an NLP system, right? Kind of similar to the vision case. Vision is used in all different kinds of security matters domains, like especially like a self-driving car, those situations. Then what about NLP? NLP, it's we also need to care about the security, because natural language processing now is used just predominantly to processing our text. And a lot of those applications are safety and security concerned. So NLP is used to process the EHR, electronic health record. It's used to detect author shapes. I mean, this is really about, IP. And it's also used to screening the misinformation and fake news. Now you may know, in the last pandemic year, there are just so big issues about misinformation online, right? We really need reliable, robust natural language processing and to help us to do better NLP jobs. So one thing is, naturally we just can borrow from the previous vision formulation to NLP, and for this adversary example, generation and robustness improvement, right? But we face some difficulties. The majority, the most fundamental issue is images are continuous, but text is discrete. So because of this, input space is so different, and you really can't use the old formulation that we had here. I mean, first of all, these X plus delta representation doesn't really work for manipulating text. It's not a summation operation at all in the original text input space. And second is our P norm. How can I use the P norm to bond a text perturbation? So how do you define the delta in the text? And how do you limit how much change is the delta in the text case? And how do you define the L? Actually, in this case, it's kind of similar, but it has a slight differences to the vision case, because the text, this variable length generation, like the machine translation task, is not totally like a classification task. And the last one, how do you optimize? Because in the end, we are searching a discrete delta. And the gradient really doesn't work to help us to directly get that best discrete delta through this gradient-based optimization. Okay, so let's just see what are the delta. So basically, there are many different choices because of this discrete space. We can do character submission, substitution. We can do word insertion or removal. We can do paraphrase generation if we have a good paraphrase model. But that's like chicken egg issues. The paraphrase model are not good enough to help us to do the semantic preserving transformation. So basically, now people actually focus the most on this so-called synonym substitution. So we just swap words in the input for a direct substitution from the nearest neighbor word until prediction changes. And so let's see why the first idea isn't the most dominating, because the misspelling, in fact, if I show you this too, True Grade was the best movie I've seen since I was a small boy. I'm actually changing to the on the right. If you just look at it, you cannot tell. You actually cannot tell very clearly. There's some changes I made. Basically, I just switched I and V in the movie word, and I changed since in the N and I into as nice. And the classifier classified this from positive to negative. This is called this misspelling based attack. So this is very interesting, but the defense is kind of easy because basically you can have just a good spelling checker. So it's interesting vulnerability, but it's an easy vulnerability. All right, let's look at the fourth approach, that first idea using synonym-based attack. So again, the same example, like True Grade was the best movie I've seen since I was a small boy. I'm actually changing it into this nearest neighbor. So it's real words, but that exactly means small boy. It's the semantics totally preserved, but the classifier classified from positive to negative. So this is a good example, totally revealed my classifier has issues. My NLP text classification is not robust. So this is most successful so far, and this is what we focus in our text attack library. All right, so enough about the background. Now this is the last phase of the talk. Also, how many minutes do I have?
There is 25 minutes in total with the questions. So
all right,
we can have 15 minutes or 20.
I think, yeah, we're good to go. All right. So now I'm trying to criticize the literature of the NLP. So the literature is a very messy, it's very messy. So many generated adversary examples, those attacks, they're claiming they have super good attacking rate, revealing the the deep NLP models to be vulnerable. But in fact, the generated examples they're generating are really bad quality. And the second is there's no standard library at all. So people just have their own repos and they compare to just whatever handy or easy to find baselines. And you really cannot tell what strategy truly worked, what strategy not, what is more important, what is less important. And they're also not clear. So as we see in the beginning, adversary robustness, it's about improving the robustness of the model. It's not about attack, in fact. Yes, we're looking for the important attacks, but our end goal is to improve target model's robustness. All right, so we try to give a solution to solve these 4 problems. Our solution is called text attack, and we're seeing we rescue the literature. Yeah, I'm making a little funny just to, yeah, it is good work. So first issue is many generated examples are bad. So let's just see what do we mean even bad. So let's come back to this formulation we use in Vision. So in Vision, we use the LP norm to bound that perturbation, to limit it to be smaller size. But in text, I haven't even tell you how do I even limit the size of the perturbation. So let's see a few examples. Again, the example we used. If we have good examples, we generate good example. This is from switch the substitute a small boy into we lad. And then here and right in the under, there are 3 bad examples I'm showing you. The first bad examples, basically it switched the best to the worst. So this still claiming to be adversary examples, but if you think about it, no, this is not adversary examples because the semantics of my original seed input is totally different from my target input. And we should not use this as an adversary example, saying this reveals vulnerability, because this is actually a correct prediction. And the issue is just because in some of the word embeddings, best has really close distance to worst, and like the attacker designer just arbitrarily use those and without checking the generated quality, generated examples. And we should filter this type of cases out for sure. And the second case of the bad case is I were a boy small. So this is totally nonsense if you think about it, right? It's just grammar-wise, it's not correct. And then last one is there's some generated average samples. It's like a minuscule. It's just sheer nonsense. It's just not human talk language, but computer will generate that. And people not filtering that out, saying this reveals the vulnerability of deep learning classifier. This is also not good. This is not quality research. So we reviewed this kind of issues in the literature's attack generated examples. So then we just think about, there's some kind of constraint ideas in the literature, but they're not standardized at all. So for example, and this we kind of extract the literature and then pinpoint in the end into a list of the constraints. Here I'm listing 2 of the constraints we propose to use. So we use what is called sign similarity between the sentence embedding of the X and X adversary examples. You can use universal sentence encoder. There are many different mechanisms providing you to calculate calculate this angular distance among the tags in the embedding space. We also propose use a grammar checker to make sure and the original seed examples grammar error and the generated adversary examples grammar error are kind of similar. So we use for example, we use a called a language to grammar checker to check the two proposed attack in the literature. We actually find the adversary example generated by this attack has much more, actually more errors than the original seed samples. And then we propose, in fact, a human-based evaluation study to guide automatic evaluation proxies. And we conduct multiple human-based like evaluations to guide. So what if we use universal sentence encoder, there's a threshold you have to define. And that threshold is very, very tricky to pick. We use humans to guide us what are the best threshold to define for that specific like automatic evaluation proxy, like in this case, USE. So we also now define the delta from the vision case LP norm into this junction form of different kind of constraint. There can be semantic constraint, grammatic constraint, character overlap constraint, non-suspicious constraint, and then you just put them together as a Boolean form. And it depends on the attackers, depend on the designer. You can do a flexible composition of the constraints, but we highly recommend the researchers should use human-guided threshold to set up their each constraint. So our literature, our evaluation actually reviewed the literature comparison between past attacks are really problematic. And what is really necessary is a comparison with the same sets of constraints and also using human-guided threshold for those constraints. Okay, so, and we then use the human-guided constraints to reevaluate those two attacks proposed in the literature. This is what we find. So this is what people reported as 91 as attack success rate, and 95 is another one. And when we constrain that constraint like a human-guided threshold, and this is what is truly obtained, the attack success rate is much, much lower from those algorithms. And this is give us some kind of thinking, is NLP models truly so vulnerable as those attack papers claimed? All right, so this is the first issue and we reviewed. And the second issue is this no standard library. So why do we need a good standard library? Because you really, without standard library, everyone has their own repo. It's hard to trust literature comparison because the implementation differences really matter. Our field is extremely engineering field. Details matter a lot. Details is the devil. And then the second is there are a lot of overlap between different attacks. I mean, with little standardization, it just really hard to reuse and hard to figure out, hard to know what is the important factor, what is less important factor. And the last one is without a standardized implementation, how can we then figure out how to use this type to make use of the library for the further goal, for the true ultimate goal is to improve the robustness of the models. We should have a standard library then to move it to the adversary training phase, which is our main goal. All right, so now let's go to the new formulation because we already know the goal, we know the definition of the transformation, we know the constraint of the transformation, we convert the vision case, that LP-based formulation into this constraint junction-based formulation. So our transformation is TX because we cannot represent the text perturbation as plus, that numerical plus operation. And then we represent transformation as the C1 to CM case. And our goal function, in fact, is kind of similar to the vision case. And then the last question is, how do we optimize this? So when we settle down with these 4 questions, we standardize our implementation into 4, which is exactly about 4, about transformation, constraint, goal function, and the search algorithm to optimize this goal. So transformation, so like we said, we're using a word substitution-centered design. And then there are many different choices of word substitution. You can use dictionary-based, you can use embedding-based, you can also use like hybrid, this kind of counterfeit embedding-based. And concretely, you can actually check out our implementation using this in our library. And this is concrete how we implemented what type of embedding we use. We use WordNet, HowNet, counterfeit embedding, graph embedding, mass language model. You can also super easily to try your own embedding, like a Jensen embedding, if you're interested in that more. And constraint, we provide word embedding, similarity-based constraint, part of speech consistency-based the constraint, and the sentence encoding-based constraint. Our thresholds are guided by the human studies. And then the goal function. So in fact, goal function, like I said, is similar. They're untargeted and targeted. There's also some differences in the sequence to sequence case. For example, you can just specify a targeted word in a generated word, in a sequence of generated word. So we provide multiple more choices in that goal function formulation. So feel free to check out in our library. All right, so last part, search. So how do you optimize this? And I'm going to talk about a few more in the next phase. So now you understand. So a search is to search the space of transformation for valid, successful adversary examples, just to kind of explain a little bit more. In the end, and this is our library, each one of the package corresponding to one of the function in this optimization formulation. And we standardize, so in summary, we standardize the tags and provide a benchmarked simulation platform to standardize the attack and enable the new attack to be easily built. Okay, so let's see how do we enable that. So we re-implement the literature attacks actually. So in a total of 18 attacks in the literature inside our library. So this is example, and it's a good, pretty good attack called text folder. And this is their algorithm blocks from the paper. So basically, we just extract all the 4 components into their algorithm implementation. And we standardize it, implement it as this in the right. So what is its goal function? We use the goal function like untargeted goal implementation we had. What is the search method? We use the Grady word swap, which is what they propose, and we implement it as one of the search. What is the transformation? What is the constraint? And then you can just do the same to all those attacks in the literature and providing a benchmark standardized way to implement all the attacks. So this is our library, so feel free to check it out and install it. It's super easy to install. So I have to say, the majority of my career was not this kind. And this is the first kind we are spending so much engineering efforts building a library. And honestly, I feel it really paid off. I mean, with so many users, I feel a lot more satisfied. But honestly, this just takes so much more time than just a paper, actually so much more. All right, so we also at the same time shared 82 pre-trained models just to help users to play with our library. And our library can attack any model on the model hub on any data set from the Nlp. And we just trained our customized model on all the glue tasks, and we shared on the Hugging Face hub page. So in the Hugging Face, you can share your own model too. So in summary, TextAttack is an open source model agnostic library for attacking and standardizing. It includes 18 popular attacks and it's easy to add other new attacks. It has 82 pre-trained models. And the last part, Osna, how many minutes do I have?
You can take, since this is the last talk, you can go as far as you want. I mean, normally we have 10 minutes, including the questions, but there are no questions right now in the QA. So
I see. I need just 5 minutes.
Yeah, okay,
I will.
5 minutes is perfect. Yeah.
Okay. All right. So then the third question is there's no clear benchmarking insight because there's no good library. So our library really enabled good benchmarking insight, which is our next paper. So why do we do this benchmark insight comparison? It's for the purpose to develop defense. So the whole idea, actually, it's about the last part of this optimization formulation. So how do we optimize this? So in the vision case, you can use gradient. Gradient gives you the best direction. But in the NLP case, because of this discrete combinatorial nature, you really just can't. Rather than, because we normally need to substitute a set of words, but in the input, you have many words, right? In the end, it's about which word to substitute to what. And so basically, this is a combinatorial search problem. So in this case, if you first flip the movie, you can also first flip the good. And these are really different paths. The different paths, maybe like which path do you take the first? And which is this path give me the adversary example in the end or not? So these are all the part of combinatorial search problem. It's a very classic combinatorial search formulation. So why do we care? Like I emphasized before, because we want to have fast generation of adversary examples to help our adversary training. If our search takes so long and there's no way to explore enough examples, and we really fail in our ultimate goal to improve a model's robustness, right? And then the concern is, so how can we have good speed and also good attack capability? And search algorithm is the one actually controls a natural trade-off between the speed and capacity. So what is search? So which I already emphasized before, but we can visually think about this kind of space of allowed perturbations. The reason is we also like emphasize in the constraint, right? So we're not searching arbitrary substitutions. We're searching those perturbations that satisfy the constraints that we enforce, because we are looking for adversary examples. If in our case, we want to preserve the semantics, and we have multiple constraint terms that define the search space. So when I'm doing this random permutations, actually not random, this heuristic driven or guided permutations, I may go out of the space, and those are not good. I need to like limit myself in this search space, in allowed search space that are also adversary example at the same time. So, and then there's this, when you have a relaxed search space and there are more adversary examples and easy to find. When you have a very restricted adversary space, search space, it's much harder to find adversary examples. As our human threshold guided constraints, in general, our search space are much more strict than the literature used. So, which is actually the reason why, like, I think literature kind of overemphasize the attack success rate and overemphasize the search algorithm. They should pay more attention to constraints. All right, so So these are the search algorithm pretty popular in the literature. There are beam search, there are Grady with word importance ranking, different kinds, genetic algorithm, particle swarm optimization. Feel free to check out those. And then, and problem is they are inconsistent. There's no clear search space definition. And our benchmark insight is optimal search is really the beam search. If you only care about text attack success rate, search algorithm matters less than the transformation and constraint. But when you're within a small query budget, which means you have a very tight time budget, and a Grady with word importance ranking is the most effective. All right, so last one is about no clear benefits. This is our ongoing work. I will have only one slide about it. So using adversary example generation and the adversary training inside the adversary training loop makes this whole procedure extremely slow. So the collection of recent work, they don't study whether that's the reason why, because it's so costly. Recent literature, in fact, don't have much results on adversary trainings. The benefits, is it clear how adversary training defend against adversary attacks? So because it's just very super costly. So this is the literature on the NLP, and so literature has really fewer work on adversary training and has a lot more on adversary attacks because of the cost issue. And also the recent adversary training work is mostly in the embedding space because the input space is just very hard to handle. So this is the popular use adversary robustness loss function. So I'm going to skip it. And we propose, in fact, in our under review work, we propose a faster tag that suit for this vanilla adversary training. And there are many engineering tricks that actually make this work. So we observe that just the first in the literature, adversary training can help improve adversary robustness against like transferred attacks, those attacks not trained on the model, which is kind of surprising. Adversary training and can improve also generalization, both the standard accuracy case and also cross-domain, the domain adaptation case. We also observe adversary training can improve a model's interpretability. All right, so that's all I want to talk, like rescue the 4 issues. And if you are a researcher, feel free to use text attack to generate your own attack. If you're a machine learning practitioner, feel free to use text attack to understand limitation of your model and use adversary training to improve your model. And also, actually, we have one more function. It's called data augmentation, because essentially adversary example is just generating hard augmented data examples. So we provide actually many more other functions to do data augmentation in NLP model training. And thank you. So this last page acknowledge, so mostly this work was started from 3 undergrads in my group. They are fantastic. I just have to say, I'm just so fortunate to have all these 3 undergrad. So one of them continued the master, and the majority of the code were coded by undergrads. So if there are undergrads in the audience, I really encourage you to think bigger, try. I mean, and this current phenomenon really enables undergrad students the good platform. You can do a lot. You actually can do really great work. All right, so that's all. Sorry for taking a little longer. Thank you.
Enjoyed it a lot. Thank you, Yanjun. This was a great talk.
Sure, thank you.
We welcome questions. If you have questions, you may write in the Q&A. If you can write it in Turkish, I can also translate it. If in the meantime, I can maybe ask a few simple questions. I mean,
sure. Yeah.
Not actually working on this topic, so these could be a little bit naive. So one thing is like for these, are there also attacks like order attacks? Like if I change the word order, or
you can switch. Yes, that's you know, shift this.
Yeah. Is it equivalent to multiple insertion or like?
Yeah. So the current literature, so at least in this literature, people, there are actually people tried, not totally yet. I think that's a very good direction. It just, I think we're heading there. The issue is like which word to swap, right? So people already tried that in a character level, but character level is so simple. You have this clear word boundary there. You just figure out the word to swap, the characters to swap. But when you have words, do I only swap neighbor words? Do I swap words in a faraway words in the same sentence? It's a very complex combinatorial search. It's actually even more costly than our current word substitution. So it's really heading there. And I think that will be a much stronger and costly attack. Yeah, I think it's a great question. Yeah.
On a related topic, so this afternoon we had a couple of talks, very good talks on interpretability, explainability.
Yeah, all right.
Like, can we make use of those tools, like which words to change?
Yeah, that's totally. In fact, because I tried to switch, you can actually use the important words being found by those interpretability method. You do substitution there. So this, let me see, yeah, right here. So, so in fact, like the second approach, Grady with word important ranking, use very similar strategies like interpretability. So I'm trying to figure out to rank the words in my current inputs. And then this ranking, how do you rank it? There are different ways to rank, right? And then this problem basically is an interpretability task.
Okay.
Yeah, so we're in the attack, we're using that interpretability ranking as a subcomponent.
I see, I see. Okay, I have one last question.
Sure.
So you mentioned this attacks where you just change the characters, but you said it's very easy because we can just use a spell checker. So
yeah.
While you were describing that, I kind of found myself thinking about the biological NLP model.
Yes, that's that.
Sequences, right? Which you are also.
Yeah.
So, and there, so imagine that we have sequences that we want to classify. There, let's say there is a change, a variation, and in a nucleotide position or an amino acid position, it's hard to tell whether this is a spelling error or it's a sequence read error, right? So in those contexts, it would be, I guess, not that easy, right? Have you?
It's actually extremely hard because in this biology, we can think about we're expanding the natural language definition into biological language, right? In the biological language and all the techniques here, we actually can use it to perturb. We try to perturb a certain like base pair positions into some other nuclei, just some other letters. But the issues I feel like there is the natural language processing, you have this massive linguistic knowledge there. And people understand a lot. I mean, the general user understand it too. In a biological world, I mean, you really don't, if you perturb, and people actually call that mutagenesis, if I remember correctly. They perturb every positions into one of the other three letters, and then to see what's the influence maybe to gene expression prediction or to transcription binding or epigenetic binding. And by that way, you can figure out what are the important positions, like the mutation positions. It's hard to say those are like adversary examples because we actually do not know. I feel like adversary example is here reviews vulnerability of the classifiers because we know the truth. We have a human person to judge the truth. But in the biological case, how do you know the truth?
I guess we need fast functional assays. But
yeah, that's a really good one. If we can hack biological functional assays, give us the truth and kind of guide us to then perturb. I mean, that kind of guide, I mean, which position to perturb. And those are the important mutation positions. And so I think this can give us location importance, and also at that specific location, what mutation is more, gives more effects in the regulatory downward pathways. So I think this whole framework actually will work. I'm actually very confident. It just the true data, the truth.
Yeah.
Is it easy to get the truth data in the biological language labeling case? Yeah. Is it available? If it's available, yes, please. I think I encourage all the researchers, we should expand our library into a biological language attack. Yeah.
So this library seems extremely useful. I'm sure this is going to be of interest to not only students, but also we have people from industry listed.
Oh, okay. Great. So, yeah. I hope this is not too basic to those people. Yeah.
So but do you only support English at this moment? I'm guessing.
Only... Oh no, we have multiple languages. We try to add multilingual now. We already have French. So one of the just contributor, she added French there, and we are trying to add Chinese, Korean, because we have like developers. We try to add, I think one more Spanish, because we have a Spanish speaker here. If some of the speakers here, some of the audience, you are interested, please add Turkish there, because I just can't, I don't know that. Yeah.
I mean, the Turkish NLP community is growing. I mean, we used to have a small community. Reyhan is actually here among the organizing committee. She's also from CMU LTI.
Oh, wow, perfect.
I don't think you have overlapped in the years. So, and she just commented, sure, we will happy to do our part.
Oh, great. Thank you. We really need people to help. I mean, because like I said, this starts from 3 undergrads, which is not like the classic pipeline. We have grad student, faculty member thought about the ideas. I have the ideas, but I don't have grad student around that time. So our undergrad helped, and they are fantastic. I mean, the way they are engineered make this such a great library. I feel like a grad student has this paper bag in their shoulder, cannot have so much, like it's just not their best interest to put on the library. But this that's why I feel like undergrads, you have a lot of rooms to play in the current research. Yeah.
Maybe they can contribute from here to that.
Yes, of course. We actually have
this time, right? We can
totally. Yeah, totally. We have contributors all over the world. In fact, I think GitHub is such a fantastic platform. It's just really international. Feel free to do the contribution. I'm going to review your pull request.
Okay, great.
Great.
So this is going to be end of today, and I want to thank you for accepting our invitation. This was really nice, and it was an honor for me to host you.
Thank you for giving me the opportunity. Yeah, I love to share this work. Yeah. Thank you.
It would be great if you share your slides with us, if it's not a problem, because
I will. Actually, I will. Yeah.
And this is something you do often, so I don't think
okay. No problem. Yeah.
So and then audience can reach out the slides and all the references from the slides. Yeah. Okay, great. So we are for the attendees, we are going to have the 3rd day tomorrow, and it will be about high performance computing and machine learning. So looking forward to meet you tomorrow morning. Okay, bye-bye.